All right, we're going to work a problem from Chapter 5. This is hopefully a kind of a straightforward problem about, this is problem 35 from Chapter 5, so that would be, turn our pen on, 535. The question reads, a 100-kilogram crate rests on a thick pile carpet. A wary worker then pushes on the crate with a horizontal force of 500 newtons. The coefficients of static and kinetic friction between the crate and the carpet are 0.6 and 0.4 respectively. Find the magnitude of the frictional force exerted by the carpet on the crate. So we have a box, a crate if you will, that is on some surface, and it has a mass of 100 kilograms, and there is a worker pushing on that with some particular force. This is the force of the worker on the box or the crate. That's clear to see. I mean, you draw bigger pictures, obviously. I'll draw the force diagram here in a minute. It tells us the coefficients of static friction and kinetic friction. That's what these values are. I mean, again, it will always be the case, but it may be worth noting that the coefficient of kinetic friction here is less than the coefficient of static friction. It tells us that the horizontal force that is pushing here, the force of the worker, the weary worker on the crate, is equal to 500 newtons. And it asks us, find the magnitude of the frictional force. So what is the magnitude of the frictional force here? Well, you might ask yourself, well, I can't find the magnitude of the frictional force. I need to know whether or not it is moving, because if it's moving, then I would use the coefficient of kinetic friction, but if it's not moving, then I would use the coefficient of static friction to help to figure out this information. So what are we supposed to do? Well, what we first need to determine, you might guess what my first step will be, and that is to draw a force diagram to look at what are the forces acting on this and the relative magnitudes of those forces. So we have we model our crate as a particle, and it has the weight, which is pushing down, or rather the earth is pulling the crate down. So this is the force of the earth on the crate. And we know that that is equal to mass times gravity. We also have there's no acceleration in the vertical direction, so we know there is also a normal force of the force of this place, maybe of the carpet on the crate. I can label these. It's probably annoying that sometimes I label these very carefully and sometimes I use abbreviations. I apologize for not being horribly consistent, but sometimes I find it useful to write it out, and sometimes I know what I'm talking about, so please use discretion as you label yours. The more that you put down for words in your subscripts, the better off you'll likely be. And then there's one more force that we know of for certain that is pushing to the right. We know the actual magnitude of this. I'll just draw some arrow. Now this arrow is we're not really sure what the length of this arrow is, but we know that there is some arrow here of the force of the worker on the crate. Okay, and that worker, I have it drawn to the left. It doesn't specify a direction, but I usually have, the direction of interest here for me will be to the right. But there's also going to be a frictional force of some type, either a kinetic force or a static frictional force that will be pushing back and to the left. And so we need to determine what that is. We need to figure out something about what that is, right? So there's something here, and I'm going to draw something in equal length here, and I'm going to put the frictional force and put a question mark here because I'm not really sure what that force is going to be. Well, how would we figure that out? Well, we know that the force, we know that there's no acceleration in the vertical direction, so we don't need to write down, we could write down something about the net forces in the y direction. But the only thing that that's going to tell us is that there is no net acceleration in the y direction, and that the normal force in this instance, since it's on a horizontal surface, is going to be equal to the weight of the crate. So there's not a lot of really useful information there, except, well, I guess it's not completely useless. We do determine that the normal force, the force of the carpet, or the force normal, perhaps we could just call that, minus the force of the Earth, the weight here, the force of the weight is going to be equal to 0, and so we know that the normal force is equal to the force due to the weight of this particular object. All right, and so that lets us know that the normal force for this instance is also equal to mass times gravity, which isn't always the case, because sometimes we're on a path that is on an angle or something like that. So I misspoke before. There actually is some quite useful information that we get out of determining that there is no acceleration in the y direction. We also know that the maximum, so if we consider for a moment, we need to know whether or not this is moving so that we know which of the relation, whether we use the coefficient for kinetic friction or the coefficient for static friction. So the static force is always going to be less than or equal to mu s times the normal force. Right? The kinetic force due to kinetic friction will always be equal to, exactly equal to, the coefficient of kinetic friction times the normal force. So if we can figure out, the first step here is we want to figure out whether or not this force is stronger than the maximum possible static force. Because if it is larger than the maximum possible static force, it means that it was strong enough to start it moving, and then we would use the force of kinetic friction, the relationship there, and then the coefficient for kinetic friction to actually determine what the magnitude of the frictional force is going to be. So let's do that. Let's figure out what the maximum is here. So we're going to solve, we want to know what is the maximum static force that's going to be applied. So the maximum static force is equal to mu s times the normal force. And we want to know basically if is that going to be greater than whatever this force is that the worker is pushing. And if that's the case, then it's not going to be moving. So let's figure that out. We have 0.6 times the normal force, which is mass times gravity. The mass here is 100 kilograms times gravity, which I'm going to use 10 meters per second squared for this because I don't have a calculator handy and I want to be able to get a quick estimate of this and show you how this problem is working. So we have, this will be 100 times 10 would be 1,000 times 0.6 would be, what is that? That's going to be 600, that's kilograms, 600 newtons. So the maximum possible static force that that the carpet is going to exert on this box is 600 newtons. That is greater than the force applied by our worker on the crate. So is this going to be moving? No, it isn't, because there isn't the force due to static friction isn't equal to 600 newtons. The maximum possible static frictional force is equal to 600 newtons. What is the actual static force due to I screwed up my words. What is the actual force due to static friction? It is equal to the force that the worker is putting on the crate. Because we know that the static friction is going to be large enough so that there is no movement, up to its maximum value. So the force due to static friction is going to be equal, well, what we would write is we would say, all right, well, we know that this force is less than the maximum static force. So let's write the net force in the x direction. We know that, now we know that this is not going to be moving, so this will be equal to 0 newtons, and we have the force of the worker pushing to the right, the force of the worker on the crate, and we have a static frictional force pushing back to the left. And that is going to be equal to 0 newtons. So, what is the force of the static friction? We have minus the force of the static friction is going to be equal to, bring this over to the other side, the force of the worker on the crate, only in the opposite direction. So the force of static friction in this particular case is going to be equal, or the magnitude rather, of the force of static friction is going to be equal to the force of the worker on the crate, which is what we needed to know, the magnitude of the frictional force. Okay, so that is equal to 500 newtons. Awesome. 9 seconds ahead of time.